Hi everyone, I'm very happy to be here and thank you for hosting such a great event. And today I'm going to talk about a research work that we did called System Risk Mitigation, where we use a two-stage network optimization with network clustering to find the best, to find a community and then optimize each community to mitigate the system risk. And here's the link of our paper. If you're interested, you can take a closer look. And here are also my co-authors. I'm the guy in the middle. So so a little bit about me. So I graduated from University of Toronto, where I worked for research on machine learning for operational research. And I also did some research on option pricing with quantum state evolution. And also did some research on getting the salted deep tabular model with borderless AI. And also I failed a startup company as a CTO because we ran out of money. And now I'm working as a machine learning engineer researcher at a stealth mode company in a Bay Area working on large language model and hyper network. So that's about me. And my LinkedIn is here, so happy to connect. All right, so back to research. So today I'm going to talk about system risk mitigation, right? So I'll first talk about what is system risk or cascade failure, and then the goal of our optimization approach. So we want to make network stronger, basically. And then the method, so the network structure optimization method that we have, and also a two-stage approach that can address some of the concerns of the original optimization method. And then finally, the results. I'm going to show the results for random networks and also the real-world network built from real-world financial data. All right, so let's go. So for the motivation, so what is cascade failure, right? So imagine now you have a network, let's say with 3 banks, A, B, and C. So bank A can, in a very simple setting, so bank A can lend some of its assets to bank B in exchange for, in exchange for shares, for instance, or holding. And similarly, bank B can lend some money to bank C, right? And now everything's good, but then what if there's some financial shocks? So that, for instance, the bank C's asset value drops by a lot. So bank C now cannot pay the $6 million back to bank B, right? And in a very simple setting, the bank C can just go to bankruptcy or basically crashed. And in that case, now bank B has the trouble of getting this money back so that it cannot pay back this $4 million back to bank A. So it also can want to go crashing. And then now the bank A has the trouble, And then if bank A also have some liabilities to other banks or companies in this network, those banks will also, or companies will also suffer from this loss, right? So we can have a very huge network. And then these failures will just cascade through the network, and then you have waves of banks crashed. So that's really bad. And how to model that mathematically? Well, we use a model developed by Eloy in 2014, where it's basically saying that the value of banks come from 2 parts. So first part is the primitive assets. So banks can hold some primitive assets. And the second part comes from cross-holding between banks, right? So this is and then basically this CIJ term is the cross-holding matrix. So CIJ is basically the percentage of bank J held by bank I. So that's cross-holding. And D is a matrix just specify the assets holding. So we can put it in matrix form. So it can be, so it's very clear that the value of banks come from 2 terms, right? So assets holding and also cross-holding between other banks. And we can put it, we can do some matrix manipulation. And in the end, when we really calculate the value, we need to discount the value calculated using this equation with self-holding matrix, which is a C hat here. So self-holding matrix is a diagonal matrix where the diagonal terms are just the percentage of the bank that is the percentage of bank that still belong to itself, right? Because it's cross-held by other banks, and then some of the percentage still left. And we need to do this discount is because that when we calculate the value, we already consider your own assets holding, and you're also cross-holding other banks. But when we calculate the value of other banks, they are also holding this particular bank. So there's kind of a circularity in the value calculation. So we need to do this discount with C hat. That is a common practice. And then how do we, this is basically how we calculate the value, right? But then how do we basically have this cascade simulation inside? It's basically through here. So again, this initial field terms are just basically from left-hand side, right? And then we have this B term here, which is kind of a discontinuous value loss. So this is where we kind of can inject the cascade failures or system risk inside, where this is kind of a vector additional penalty for the value of the banks. So for instance, this B vector can be simply defined as this. So if the value of this particular bank drops lower than some threshold, we're just gonna set, B is equal to some fixed percentage of its current value, and then drop that from its current value, right? So it's modeling kind of like the public losing faith on this bank or on this company, so that there's gonna be additional penalty because its value dropped below the threshold, right? So it's kind of like an additional discontinuity that we add to the model. So our goal here is that basically, given that sort of like the formulation of cascade failures. Oh, by the way, let me talk more about how we can do cascade simulation with this. So we can first calculate the value of the bank without this B term, and then we have some initial perturbation, let's say on asset value. So the value of some banks dropped below the threshold. And then for those banks, we're just gonna have a B vector applied on them, right? And that B vector is a loss of their values, and then that loss is shared by other banks because we have this cross-holding, and then that initial kind of like shock will lead to this initial loss of bank value will be shared between all other banks, and if more banks' value drop below that threshold, we just can have more B vector, and then we'll just keep doing that calculation of values until everything stops, and then like many banks crash. So this is the cascade simulation environment that we have, and based on this modeling, our goal here is to optimize the network structure so that it can be stronger to that sort of like cascade, right? That's our goal here. And then we test the performance or the effectiveness of our optimization with this cascade simulation. And here's just one visualization. So we have a random network. Initially, some perturbation lead to 5 banks crash. So there are 5 black dots, which are just banks. And then we can just recalculate doing this cascade waves, right? And finally, we find that all those banks crashed. And then we can count how many banks crashed, and then plot that against the initial perturbation level, right? So we can get this phase transition where at this middle range, it's really, the total number of banks crashed in the end really grows really drastically when the perturbation level grows, right? And the goal of our optimization is basically push this phase transition to the right. So that means like the network is more robust or stronger, or stronger towards system risk. So that's our goal here. So how can we do this optimization? So initially we designed optimization look like this. So so here, the decision variable here is just the Cij. So we're just saying that, okay, now I'm just gonna use cross-holding directly as a decision variable where the Cij is the percentage of J held by I, right? So this is kind of like determined by J when it's issuing steps, for instance. And basically this term is also related to bank I's loss when J crashes, right? Because Cij is the percentage of J held by I. And then remember that B vector, right? So the B vector, for instance, if bank J crashed, it's gonna have its own discontinuous loss, and that loss is shared by bank I proportionally to the Cij, right? So this is why we are using this as decision variable. And with that being decision variable, then this inner sum, where we sum over I, is basically the total loss of all other banks because we sum over I, right? So total loss of all other banks due to bank J crashes. And then if you have this other sum, then it's basically the total possible loss of all the banks due to crashings of all the banks, right? So this objective function here is basically kind of like the worst scenario. So like we're optimizing for worst scenario. So like if all the banks crashed, what's the total possible loss? And then let's minimize that loss. And then the 2 constraints here is just making sure that some financial properties like exposure or the self-holding doesn't change. So we want to change the C matrices, but we don't want to change too much of its original depth structure, let's say, or like some financial properties. And all right, so this is kind of like a initial optimization scheme that we have. So there's no 2-stage; it's just one-shot optimization. But there are some few concerns here. So first is that the scalability of this approach, right? So remember, it's like here, I didn't mention it before, but here we have this minimum calculation here. It just makes sure that banks cannot have loss bigger than their original value, like their total equity or the original value. Like you can just go 0, right? You won't go negative. So that, so in order to handle this in this optimization, like in this linear programming, we need to basically do some adding more accelerated decision variables to turn this optimization into a mixed integer programming problem. And that, basically for MILP, in general, the effort of solving grows very fast according to your number of decision variables. And our number of decision variables, which is CIG, is actually n squared, right? So n is number of banks. So for a large network, this is very like computationally expensive. I'm going to show the time comparison later. So this one shot, it's not very efficient in terms of dealing with large problem size. And another concern is basically this. So we have this initial network, and then we can use this one-shot optimization to optimize, and then this is what we get in the end. So you can see that there's kind of like a drastic change to how banks connect to each other, which can be impractical because banks really need to adjust their depth structure, right? So in this case, it's another concern for the method that I just described. And now we are just thinking of a way to deal with this concern by a divide and conquer approach, where it's kind of like the two-stage approach in the title. So so basically we divide the original network by first doing some community detection to find each community or modules, and then we just optimize each module. I will explain the motivation later, but that's how we get this two-stage optimization approach. And then for clustering, we can use different clustering algorithm. For instance, for quantum, like we use quantum annealing, that we find empirically that in our context, it gives best result, but we can also compare it with other clustering method. So with this divide and conquer approach, we're dealing specifically for the first concern, the scalability, right? So for each smaller module, the problem size really shrinks. And then we find that with that approach, it's actually really make the second concern better, because now the changes of the network cross-holding isn't that much anymore. So I'm going to show that soon. So what is this two-stage again? Well, so again, now I'm going to talk about the two-stage optimization with quantum clustering, right? So it's our final approach. So the two-stage works like this. So instead of having this one-shot optimization directly on the network from the start, we first do community detection or clustering, where it's the same network. I'm going to show now different modules, which is 4 here. And then for each module, I'm going to apply this one-shot optimization. So I'm just going to kind of like optimize the cross-holding within each module without thinking about how they are connected between the module. And then why would this work, right? So why would this work? So now I'm going to study the process of cascade failures first. So this is, again, I already showed this simulation, which is just on the same network, and then this is a cascade process. And then I'm going to show the same network with the modularity, with communities shown with different colors, and then do the exact same perturbation and the exact same cascade process to see what happens. So at first step, this bank's crash is the same 5 banks. And then second time step and the third time step, right? And then all the way to the fourth time step, we can see that this module or community on the left, it still hasn't got one failures yet. All the failures or cascade happens within other modules. So what this means is that the cascade failures kind of like spread within each community first, right? And if you think about it, it makes sense because the B vectors, the loss, is shared across the network with the C matrices. And when we do community detection, we're actually based on the C matrices as well, right? So it's almost like the cascade failures happens within each community first. And then the community detection now becomes a method for locating the source of that cascade failures. So that's why this is kind of the motivation for two-stage approach. And now it comes to the quantum part. So why are we using quantum? So initially we're not sure which is the best clustering algorithm to use. And then we find that there are many works showing that for this quantum clustering, it really shows superior performance compared to classical methods, and they have their reasoning. And then we tested it out. It's indeed the case in our context. So basically, how we do this with quantum annealer is that this community detection part have its cubical formulation. So basically, the formulation is here, and then we can. So now the decision variable is actually xij, where if x is a binary decision variable, where xij is 1 if bank I is in community J, right? So that's the current formulation. And then we can, basically from the from this banking network, right? We can have this cubical formulation, and now each bank I gets mapped to 3 binary decision variables. If bank I is in cluster 1, if bank I is cluster 2, and if bank I is in cluster 3, right? And then that gives us a Hamiltonian graph, which is kind of like similar to cubical, but then you need to do some transform of your decision variable to make it -1, 1, right? Things like that, so that you really have this correspondence between each spin particle to the system variable directly. And then we can use this, Hamiltonian, which is just related to this Kubo formulation, as your final Hamiltonian of your quantum annealing process. So for quantum annealing, right, you start with a very easy to build. Basically, you start with some initial Hamiltonian whose ground state is just basically, it can be like just all superposition, like uniform superposition, and that's a state very easy to prepare. And then you slowly, you kind of like slowly anneal your Hamiltonian from initial parameter, your initial Hamiltonian whose ground state you already prepared to the final Hamiltonian, which is your problem over here. And quantum annealing works because if you anneal that process slow enough, if you change, the magnetic field slowly enough, then your quantum state will stay within ground state. And in the end, we have a problem Hamiltonian, so we have a ground state for a problem Hamiltonian, so that we have kind of like the optimal solution for this Kubo problem. So that's quantum annealing. And basically we find that quantum annealing give us kind of like more accurate communities. For instance, for this one, it's a classical algorithm like Lauven. And then for here is the with quantum annealing, like we can see it like slightly more accurate. And here I'm going to show the results of time comparison and also the cascade simulation comparison. So here it's basically comparing four methods for whether the network is stronger or not. This is kind of like pushing to the right phase, pushing to the right phase transition, right? So to make the network stronger, to show the network is stronger. So like we have the random initial random network without any optimization. Then we have this one-stage optimization and two-stage optimization with either classical algorithm or quantum clustering. So the quantum clustering is to the right most, and then this one is kind of like the two-stage with classical, and then this one is the this one is the one-stage, and this one is the two-stage. So we see that, all right, so it's really pushing the phase transition to the right, so that's good. And one more interesting thing I want to say is that, sure, so yeah, then let me skip this, sorry. Yeah, so let's just focus on the postpone of the phase transition. And in terms of the time, we can see that, the two-stage with quantum partitioning really gives the time, it's the most efficient. But here, we are really just taking the time of, for quantum, we're really just taking the time within, of solving time within the solver, right? We're not really considering time of like sending this forward and backward with D-wave. So yeah, I'm not sure whether it's a fair comparison, but we really just need the solving time. Yeah, so let me skip this. Yeah, so this is the final slide I want to show. So remember, we have these two concerns about scalability and like basically also the changes of cross-loading is too much. So now with the time comparison, the scalability is solved because, for instance, like for this one, we can see that we are like the time that we have right now, it's really we're doing much better compared to the original one-stage optimization. So, but what about the second concern? So for second concern, now we see that with this two-stage approach, the changes are much simpler compared to, I mean, the changes are much less compared to the original one, because now we're just doing things within each module that gives us less drastic change. All right, so sorry for went over time, and thank you everyone for listening. And yeah, thank you.
Let's thank